how these are the most important group of minerals, especially for geologists, because they're the most important rock-forming minerals. So a lot of the rocks we'll study will have these silicates. They're 95% of known minerals. 75% of the Earth's crust is made up of silicon and oxygen, and that's why silicates are so important. And the basis of silicate minerals is silicon and oxygen in this arrangement. So you have a silicon atom, and it's shared in 4 corners bonded in 4 corners to oxygen atoms. So imagine this in 3D, and this is called your silica tetrahedron. And each of those bonds here is a covalent bond. So what they're actually doing is sharing electrons between them, etc. And so what you might be asked in an exam or in future is just to be able to make sure you can draw that arrangement. And what you'll actually find in a lot of textbooks and a lot of things that I post is it drawn in 3D. I'm not going to be able to do this, am I? And they sometimes even draw it going back, like that. But basically it's like a pyramid structure with a silicon atom in the middle, surrounded by 4 oxygen atoms. So that's the silica tetrahedron. Or you can call it silicate iron. Because each of those oxygens has an overall charge of 2 minus, so if you add it all up, the whole thing has a charge of 4 minus. And this is really important because this 4 minus overall charge of this ion needs to be balanced. So then you can bring in your cations, so calcium 2 plus, Mg 2 plus, sodium, whatever cation you want, and it bonds with those ionically to balance the charge. But this is the important thing, the silica tetrahedron, otherwise known as a silicate iron. But the tetrahedron part is important because that's the pyramid arrangement. So that's simply the first question. So if you were to ask that in an exam, draw a simple diagram to show how silicon and oxygen and silicate atoms share electrons, something like that is fine. And so the next question refers to this process that I introduced called crystallization. So as we know, a mineral has to have a crystalline atomic structure. It has to have this repetition of atoms in an ordered way. And how that starts is you have your minimum number of atoms in your unit cell coming together in the appropriate arrangement. And then all the rest of the crystal grows around that. So you have a nucleus, a microscopic crystal which we call a nucleus. And then the atomic arrangement builds up around that nucleus in a process called crystallization. And the formation of that microscopic crystal is called nucleation. Okay? So the next question says, in some bodies of granite, so granite is a type of igneous rock formed deep underground, which is cooled very slowly, so you tend to have large crystals in it. And in some of these bodies of granite, we find incredibly large crystals, and we call these pegmatites. So this is a type of granite with very, very, very large crystals. The largest crystal in a pegmatite is 10 meters across. So it's one crystal of feldspar which is 10 meters across. And I think in my question it says, yeah, we find some very large crystals, some as much as 1 meter across, the largest in the world, 10 meters across, and yet these crystals tend to have few crystal faces, What do we know about the conditions under which these large crystals grow? So first, if we focus on the large, basically it must have had a lot of time to grow. You can't grow large crystals unless you've had time for that nucleation and then crystallization around that crystal to build crystals of 10 meters. That's just, yeah, you need a lot of time. So very, very slow crystallization. So, long time. And I told you there were lots of ways that you can cause crystallization, and one of them is cooling of a liquid, and pegmatites and granites formed by cooling of magma. So we're talking about very slow cooling magma. Large crystals can grow. And another thing, I won't go into this too much, but these nuclei, like microscopic crystals from which bigger crystals grow, if you have lots of nuclei, each of those crystals grows. But even if they cool slowly, eventually they're going to compete with space with other crystals, so they can't grow too big. So if we have crystals that are now, we're talking meters across, there can't have been many, like the concentration of nuclei can't have been very big. And that's what we think how pegmatites form. It's where you get a lot of crystals that are suddenly diluted by something like water, and we call that high diffusivity. Don't focus on this too much, but high diffusivity. Diffusion is literally the movement of something at high concentration into something at low concentration. So it's where you get a magma with lots of nuclei being diluted. But don't worry too much about that, worry about this. The other point in the question is that these pegmatites, they're not perfectly formed crystals. They might be big, but they don't have perfectly formed edges like this. They're quite often more rounded, even though they're big, so they've had a lot of time to grow, but eventually they're competing for space with other minerals. So, eventually competing for space. But this is the key thing, very, very slow cooling. So the next question, if that's okay to move on. Yeah. Okay. What physical properties of sheet silicates are related to their crystal structure and bond strength? So first of all, I'll redefine sheet silicates for you. These are literally, this is where my diagrams are going to be terrible, they're sheets of the silica tetrahedron bonded, oh goodness, in 2 dimensions, so, oh goodness, don't draw this, I don't know, okay, they're sheets, these are tetrahedra, imagine they're not teeth, the tetrahedra joined side by side, in sheets, etc., and they have cations between them, so imagine calcium, magnesium, and these are there because remember our tetrahedra are charged, so each of those sheets has a negative charge. And it's balanced by cations. So within each sheet, the tetrahedra are covalently bonded to each other. So we have covalent, strong bonds within sheets, bonds within, between the sheets, you have weaker ionic bonds. And so when we talk about the physical properties of sheet silicates, they break apart quite easily into sheets, and we call this here a cleavage plane. And a cleavage is it's the tendency of a mineral to break along planar surface. And the planar surface that it breaks along is always a planar surface where the bonds are weaker. So in sheet silicates, the bonds are weaker between the sheets, and so that cleavage, it tends to only have one cleavage plane, and that's between the sheets. So basically you can break it apart into sheets, and that's the physical property that's directly related to the crystal structure. And if you haven't done the practical already, there is only one class this morning, and you'll see the micas, which is the most famous group of sheet silicates. You can literally, I tell you not to do that in the practical because it destroys our minerals, but if you want to, you can pick apart sheets of these glittery looking minerals they use to make glitter. But actually within the sheets it's much harder to break them because they're covalently bonded to each other. So the next question relates to industrial applications of minerals. So it's, if you're an engineer and you're looking for a material that's got a certain use, then you look at the physical properties or the chemical properties. In this case, the physical properties of that mineral. And in this case, you basically have steel and you need to sharpen it, you need to grind it down. So you need a substance, a mineral that can do that. So steel has a hardness of 6.5. So remember in the lectures there's a scale of hardness from 1 all the way up to 10, where 10 is the hardest, 1 is the softest, and we call this Mohs hardness scale. And we can measure the relative hardness of different minerals on this scale by seeing if one can scratch the other. So if something can scratch another mineral, then it's harder than it. Or if it can't scratch, it must be softer than it. So if we've got steel, which has a hardness around here of 6.5, but we need to grind that steel down to sharpen it, we need something that's harder than steel. So we need something towards the harder end of the scale. There are lots of minerals that are at that end of the scale. The most famous, I suppose, so quartz has a hardness of 7. It's harder than steel, but it's not that much harder, so it probably won't sharpen it very well. You could use it. Quartz is really common, which is an advantage in engineering. But I would say something like corundum. I think that has a hardness of 9, I think. Diamond has a hardness of 10. So this is the ideal, because it's much harder than steel. But diamonds are really rare and really expensive, so you could use something like corundum, which is slightly easier to manufacture, but also slightly more common than diamond. But those would be the two that I'd go for. So I guess it depends on money, like everything. I like this one. This is related to pressure and mineral formation. So I've given you the names of 2 minerals, which both have the composition of calcium carbonate. but one atomic arrangement. So one mineral with one atomic arrangement is called aragonite. Still made out of calcium carbonate. It has a density of 2.9 grams per cubic centimetre. And there's calcite, which has a density of 2.7 grams per cubic centimetre. So they both have exactly the same composition. So the reason that one of them is denser than the other is that its atoms, so it's calcium, it's carbon, and it's oxygen atoms, are packed into a smaller space. So per unit space, cubic centimetre, you have more atoms. And that's just to do with the different crystal structures. And in nature, if you have a high pressure environment, so deep in the crust, for example, or somewhere where plates are colliding, the most stable arrangement of atoms is closer together, which you can imagine. If you're pushing things together, the atoms want to be close together. So when I say it's not a foolproof situation, some minerals of low density can form under high pressure, but given everything else being equal, so chemical composition, temperature, everything, if you had to guess which of those was formed at higher pressure, it's going to be the ones with the atoms closer together, so the denser form. And this is true. You can get this forming on the Earth's surface. A lot of sea creatures, if you ever seen mother of pearl used in jewellery, that's made out of aragonite, but it's not very stable on the Earth's surface, and over time it will convert to calcite because the pressure is too low. And if you have calcium carbonate forming deep in the Earth, it tends to be aragonite. And what you'll see later in the course is that we have pressure temperature diagrams. So this is temperature on the bottom usually, and pressure on the side. Certain minerals with the same composition are stable at different fields, and I think this is calcite's field. This is aragonite. So they can both live at high temperatures and low temperatures, but aragonite tends to form at these higher pressures. I think it's something like that, or maybe it's a bit like that. Anyway, you'll see more of those as I go on. Looking at changes in density as we get down towards the core of the Earth, we get these jumps in density, but actually there's no suggestion that the composition changes, and they think it's just basically these minerals getting to a certain pressure and rearranging into denser forms. We'll come on to that in a later lecture. So this next question, it directly relates to the lab you're going to do this week if you haven't already done it. Where we have minerals that are unknown, we have to identify them. Sometimes we have to identify them in situations where we don't have access to complicated equipment because we're up a mountain and we need to know what the mineral is. So we use their physical properties. And the question's a bit vague. It says, which physical property is most useful in discriminating between minerals that look similar? Okay, it's a vague question. But say you have two minerals that look similar. Okay, the colour's not going to be a distinguishing feature because I just told you they look similar. Crystal habit, I've already told you they look similar, so maybe that wouldn't be very useful. And the example, in a case where minerals look similar, you want to look at other properties. So hardness is a great one. They might look very similar. Luster is another property. If it looks similar, it probably has similar luster. That's the way that minerals reflect light. But I just told you they look similar, so that's not great. Hardness is a good one. And like I just told you, pardon? Streak, exactly. Yeah, streak is another. So hematite is iron oxide. Quite often it's a nice rusty red colour, but sometimes it can be found in a grey sort of colour. That's bismuth, that's hematite. Brown, but it can be grey. Magnetite is Fe3O4. It's quite often grey. But this will always have a black streak or a grey streak. And this will always have a red streak. And a streak is just, you determine what the streak is by rubbing the mineral across a porcelain plate. So a porcelain plate has a hardness of 7, so anything softer than that, you can powder the mineral along the plate and look at the colour. And this is really useful for metal oxides and metal sulfides. So streak is a good one. And then we have other properties like reaction with acid, magnetism, but this is only really useful for one mineral, magnetism, so for all else of the minerals it's not that useful. The example I gave you in the question is 2 clear crystals. You don't know what they are. One's quartz, one's calcite. So quartz has a hardness of 7, calcite I think has a hardness of 3. So you can easily figure out which one's which just by, if you have a glass plate which has a hardness of 5.5, it'll be able to scratch calcite, but it won't be able to scratch quartz. That's an easy diagnostic tool. Calcite reacts with acid. Or any acid, but for HCl to form calcium chloride, or CO2, whereas quartz doesn't react. And there are other properties. Quartz has no cleavage. So if you remember, quartz is formed from just silica tetrahedra covalently bonded with each other. There's no plane of weaker bonds, because it's the same bonds in all directions. Calcite has 3 cleavage planes. And if they're allowed to form distinctive crystals, then you can tell the difference between them. But if they look similar, it's a bit harder. So it shouldn't be too difficult whatsoever. So the next question, just a simple thought exercise. So coal is formed from where you get large amounts of organic matter accumulating but not decaying. So quite often it's formed in these swamps in equatorial regions, and there's a lot of vegetation being produced every year, and that dies and it gets buried, but the waters are actually stagnant, they don't have much oxygen in them, so the organic matter tends to get preserved and buried without being decayed. And eventually as that organic matter gets buried deeper in the earth, it heats up and it's pressurized, and all of we call them volatiles, so water in the chemical structure, oxygen, hydrogen, they get driven off, and you end up with purer and purer carbon. And eventually it forms coal. But coal does not have an ordered atomic arrangement, so you can't call it a mineral. But given enough time, if you really repressurize it and increase the temperature, everything's driven off and you're just left with very pure carbon arranged in sheets. So imagine this in 2D, you get pentagon-shaped, I think they're pentagon-shaped, or they're hexagon, yeah, hexagon-shaped rings of carbon. So there's a carbon here, in sheets with weak bonds between them, and they have an ordered atomic arrangement. So we can say graphite is a mineral, but coal isn't. So it's simply down to that ordered atomic arrangement. Okay. So this one, I've given you a formula. I didn't introduce this in the lecture, it's just concept. But I told you in the lectures that you can have many, many different types of silicate mineral depending on how those tetrahedra are arranged. So in minerals where you have isolated tetrahedra, which are bonded together by cations, so I'll give you calcium, magnesium, whatever. But these are isolated. There are no oxygens shared between different tetrahedra. So that's our isolated silicates, isolated tetrahedra. An example is olivine. Sometimes those tetrahedra are bonded together in long chains. So each tetrahedra shares one oxygen with the next tetrahedra. It's like they're holding hands. They form long chains. So chain linkage. Example of hydroxines. Sometimes these are arranged in sheets, so you have in one direction, so in 2 dimension. Basically all of the oxygens in each tetrahedra are shared apart from the top ones. So they're arranged in 2 dimensions in sheets, which I've already introduced already. So you have sheet silicates, e.g. mica. And then when all of the oxygens are shared with another oxygen, are shared with another tetrahedra, we get framework silicates. Now in a chemical formula, the ratio of silicon to oxygen depends on how many oxygens are shared between the tetrahedra. So it depends on which type of silicate this is. So the ratio of silicon atoms to oxygen atoms in isolated tetrahedra is simply 1 to 4. So that's silicon to oxygen. Because no oxygens are shared between different tetrahedra. So you have, for every 1 silicon atom, you have 4 oxygen atoms. With chain linkages, it's a bit different. Just check this. So because 1 oxygen is shared, we have a ratio of 1 to 3. Sheet silicates, let me just check this, it's 2 to 5 here. And in framework silicates, it's simply 1 to 2. All of your oxygens are shared. So just looking at the formula I've given you, so we've got 2 silicons to 6 oxygens, so which do you think it is? So 2 to 6? Chain, exactly. So yeah, if you double everything here, 2 to 6, that's the same ratio as 1 to 3. So the question is, what does the formula, so I'll write the formula up here. Si2O6. This part of the formula tells us it's a chain silicate. Other part of the question, I said, what does the formula tell about its crystal structure? Cation substitution. So wherever you see atoms that form cations, so positively charged ions, and you see them in brackets with a comma between them, that's because they can substitute for each other in this crystal structure. So where you can find a magnesium ion, you can also find a calcium ion, and they can substitute for each other. That's because they've got similar charges and roughly similar sizes. So all this formula tells you is that in this mineral structure, calcium and magnesium can substitute for each other around the crystal lattice. This part of the formula tells you it's a chain linkage. So you can deduce something about a mineral just by knowing its crystal structure. Design structure, specific chemical composition, and it's, what was the last one? Inorganic, usually. In fact, I'll go through these now because we've got a bit of time. This was a short one. Just make sure you can understand all of these. So, first one. Define a mineral, so it's natural, inorganic, solid, ordered, arrangement. Specific chemical composition. Yeah, that's right. Question 2, I'm going to go through these quickly. Difference between an atom and an ion. You should all know this. So, same number of electrons as protons. So no overall charge. Because all the positive protons are balanced by the electrons. Fewer or more electrons than protons, so it's charged. If it's gained electrons, so it has more electrons than protons, then it's a negatively charged ion, so an anion equals negative. And a positively charged ion is a cation, because that's lost electrons. I'm not going to draw the atomic structure of sodium chloride, that's in the lecture notes, you can look at it. In fact, I won't even really go through the rest. What are two types of chemical bond? There are many you can choose from. So covalent is where you share electrons between atoms. Ionic is where you transfer one electron to another atom, creating an ion in both places. Metallic bonds, that's where you have a sea of electrons and delocalized electrons between nuclei. List the basic structures of silicate minerals, I've just done that. So, isolated, single chain, double chain, sheet, framework. I listed all the other types of minerals in the lecture, so sulfides, oxides, sulfates, you can list all those. And how would a field geologist measure hardness? So using tools of known hardness. Using tools of known hardness. On the Mohs scale. And then trying to scratch various minerals. That's how a field geologist figures out how hard the mineral is. So that's pretty much it for today. That's a short tutorial. But as everyone, I know some of you probably do chemistry, so it's really easy. But does everyone understand everything I've said? Yeah, I mean, like I said, all your mid-semester tests and your final exams will be based on the content of these tutorials, so it is really important that you understand them, because I might ask you to draw something that I've covered in the tutorial, so yeah. But I think relatively simple, so.